somebody told me that it was taking a while to download the book. Did you have that experience?
Yeah.
Okay. In that case, what you do is you go to openstacks.org, which is the primary site where the book has been downloaded from, and that downloads pretty quickly. So the OpenStax website's name is actually given on the syllabus, but what you do is you go to openstacks.org, which is out of Rice University, but it has a separate .org website, and you go for college physics. Do not talk. You're not supposed to talk here. So college physics, OpenStax.org website. It is on UB Learn. So if you can download, you're perfectly okay. But if you cannot download, if it's taking time for you, then go to OpenStax. It downloads quickly. There is another book that I have put on UB Learns at the same place, called Documents Page. That's the stuff on math. Because over the years, I've noticed that many people come with rather inadequate math background, which is not unusual because we have students from a whole variety of departments and schools. So if your math background is turning out to be a real problem, you should really see me as soon as possible, which means today. And if your math background seems rusty and not a real problem, then you should download the math book that I have posted, which is also an OpenStax book. And that's an excellent book. It gives you all the prep material that you can possibly need. Okay? So that's a great, great resource to have. And I encourage you to have it around anyway on your laptop, or just print out a hard copy. For the textbook though, I would urge you that in addition to having the PDF file that you do not fiddle with your phone, please. Don't look the other way. Yes, don't fiddle with your phone. You don't need to use the phone now. I'm talking to you. No, the guy at the back. Yes. So my suggestion would be get a printed copy. You can go to the library, I'm sure. You can print out several chapters at a time. Probably they'll let you do it. Even if it costs a little bit, it's much less than the cost of buying a book, which at the very least is well over $100. So please go ahead and don't delay, because I've already assigned the homeworks. The first set of homeworks you're supposed to have finished by Saturday night, because I will be assigning you the second set on Saturday itself. And next week, I'll be testing you on the material in the second set as well. The first set material, I will already start to test you on Tuesday. And this will carry on just like that. Any questions? This is a fairly fast-paced course, and the reason why 2 homeworks are due is not because I'm trying to torture you. That is not my real intention. But it turns out that that's the only way I can keep you guys. It proved to be something that works over time. That's the only way I can keep you guys from working on the problems regularly. Otherwise, all of us have a tendency to work at the last moment, which is not unusual. But when you do that, then you literally, that makes a difference between survival and failure. And the failure rate in 101 is very high. So I do not want any of my students to have trouble down the road because they are not being very systematic and conscientious. If you want, I have considered doing a crash course on a weekend, maybe a Saturday or 2 on the math stuff. That's a fair amount of extra work for me because I have to basically dedicate a significant span of time to get you ready for it. But if I have enough show of support down the road, let me know by email. I will consider it. I can't promise you, but I'll consider it. That way I can get you up to speed separately, maybe over a weekend on Saturday or something, if I can find a space, appropriate space in the university and then on campus to get you kind of up to speed on a few things. But I've never done it. I've never had a need for it. But I'm really working hard this time to see if I can minimize the number of people who end up having to withdraw or resign or drop down the road, which is never
a lot of fun for anyone. Okay? I understand that's not something that you want to do in terms of dropping, and that's designed to help you guys. The other thing I want to mention, which may not seem like a big deal to most people right now, but we have done studies over time in which we have found that the students' stress levels build up enormously as they go through a semester. In particular, when they are taking these large required courses, particularly because these large courses often, the performance in these courses often determine whether they can get into their major of choice. So I wanted to make you aware that UB has a really fantastic counseling services office, and it's run by a friend of mine who's a very accomplished psychologist. If you have never heard of her, then she's the director of counseling services. I just want you to have this info handy in case you need it. I'll give you the rest of the details. It's 645-2720. When I go in there from time to time because I work with her on various things, I always find great many students waiting there, and it's 120 Richmond Court, Susan Elliott. And they run a whole bunch of free services from counseling to yoga and whatever it is for helping students to deal with stress and anxiety, which turns out, by the way, to be a major reason why students tend to underperform or drop or fail in gateway courses. Not something that I would have thought 15 years ago or 10 years ago, but it just happens to be a fact. All right. Any questions? Raise your hand. Yes or no? No question. Yes?
The homework, will it be posted Sunday morning or Saturday night?
It depends upon how busy I am on Saturday night, but I'll try to post that. Any other questions on the physics? Okay. So I already did some stuff on Tuesday. I'll carry on from there. I'll quickly remind you of a few things. So one of the equations we set up, right now we are doing kinematic equations. And kinematic equations form the first part of the mechanics stuff that we're doing. And the kinematic equation that we dealt with distance traveled is velocity times time, or speed times time. In particular, velocity times time. So what's the difference between speed and velocity? Before I get into these in more technical manner, let me just point out that the difference between speed and velocity is very simple. When it comes to speed, direction does not matter. Direction doesn't matter. So, in other words, if I'm traveling around a curved path, let's say, from point A to point B, and I'm traveling, let's say, at some speed, 10 meters per second or 5 meters per second, then that's perfectly fine, because whether I'm going this way or whether I'm going that way or some other way, it doesn't matter. I can describe the motion in terms of speed. A little bit more rigorous and precise would be velocity. In velocity, I'm typically considering motion along a straight line in a fixed direction. So velocity and speed, they have the same units, meters per second. But when it comes to speed, your direction does not matter. When it comes to velocity, your direction does. So in this case, if I consider my velocity over here, my velocity would be in that direction. But when I make a turn, my velocity would be in this direction. And when I make a turn again, my velocity would be in that. So velocity direction is continuously changing. So that's the difference between speed and velocity. So let me just be precise and say distance traveled is velocity times time. And let me also say, as I was saying, as I was ending last Tuesday's lecture, that I can really think of this as V bar times T, where V bar is the average velocity. This means definition. Sorry, average velocity. So what is average velocity? So suppose I'm plotting time versus velocity, or time versus distance. Well, let me do time versus velocity. So I have time here and velocity here. And let's say this is time equal to 0. This is up to some certain time t. And velocity, the simple case if velocity is fixed would be that v is fixed, as I pointed out, and therefore you get this rectangle. And the area of this rectangle would be v times t, so that would be equal to d. That's the patched area. So d is v. That's something we did last time. Now what I'm telling you is I was trying to do a better lecture, if you remember. So basically said that I don't have to have this velocity fixed. The velocity can actually vary a little bit. So for example, the velocity varies like this. So in that case, if I plot velocity versus time, then this would be a jaggedy top. So I can't easily measure the area of this thing, the jaggedy top. So what do? Well, what I do is I take multiple points wherever I want, representative points, more the better. And let's call this V1, let's call that V2, etc. And then I compute a V average, which is defined as V1 plus V2 plus, let's say, Vn, whatever n may be, divided by the number of sampling points that I've used. So that's my V average. So if I use 2 points, V1 and V2, it will be V1 plus V2 divided by 2. Okay? So what you're really doing is you're replacing this jaggedy structure by a flat line, which averages the value, and you're getting the area from there. So D is equal to V bar T. So therefore, that's a nice extension. It's a very powerful extension, and we'll be making good use of this. D equal to V bar T. Again, when I told you when you write an equation, you must get in the habit of doing dimensional analysis. So distance here has a unit of length. T has a unit of time. Left and right side of the equation should have the same dimension, so you have L over T. And L over T, therefore, would be the dimension of velocity in this case, same as that of speed. No change. Any questions so far? Okay. You should ask questions. Remember, there's discretionary points for engagement. Engagement means everything. Okay? If you think that there is something that you don't quite get, I'd much rather have you ask the question and get it clarified than try to figure it out yourself later and waste time. Because time is critical. Pretty soon you'll find you have just no time to do anything. Yes?
What was L?
Huh? Is this the first day you're here? Yeah. Okay. So L has the dimension of length. So L is length. So that means this signifies length. It's a quantity that characterizes length. Distance traveled is length, right? So time is denoted by T. So this is called dimensional analysis. In dimensional analysis, what we do is when we write an equation, we make sure that the dimension on the left side and the right side are the same. So if it's not, then you're making a mistake. So it's a way you check and make sure that you're done it. Okay? Any other questions? Yes?
Once we had D equals VT, if you have two different velocities, would you have to do the
Yes.
and then you have to go through the problem like that?
Then you do that.
Oh,
That's if you choose to use that equation. You don't have to use that equation in every case. But there are certain scenarios where the equation turns out to be useful and handy. So then this becomes a very powerful tool. And we'll discuss that. I'll show a few examples where this turns out to be useful. Yes?
How do you decide as to which velocities you would use for the graph?
That's a good question. This is totally random, right? So I can take as many points as I want wherever I want most of that. But in principle, I can take two very bad points and get an average pretty low, right? This is what, if you're listening to CNBC, they always tell you somebody has blown their money by 25% or 75% by taking the worst point to the best point and got that. Well, no. So averaging is always a tricky game, and you should know. All right, we have discussed the slope business, so I'm not going to get into that. let me now do a thought experiment. Since we can't do real experiments, we do thought experiments also. Suppose this is ground level. Okay? And suppose there is a higher level here, level 1. There is another higher level here, level 2. There is another higher level here, level 3. You get the picture. So I call this level 1. So these are at different heights. Level 2, level 3, etc. So suppose you want to climb up here and drop a ball. That's you there. And you take your ball and you drop it. Simple experiment. You can do it at any time. Right? So you have dropped the ball. And you now want to find out how fast this ball is moving just as it hits the ground. So mark what I said. Now, in physics, when we say drop a ball, that's a very technical word. Dropping a ball is not a trivial statement. It has a mathematical meaning. So what's the mathematical meaning of dropping a ball? Does anyone know? Yes?
The initial velocity is 0.
Good. So dropping a ball means the initial velocity with which you're releasing the ball is precisely equal to 0. So when I say that you are dropping a ball, I'm actually giving you, in words, a numerical detail that the initial velocity is 0. If you forget that, you're in big trouble, okay? Because we'll be using it all the time. All right. So when I say I drop the ball, the initial velocity is 0. All right. So let's say initial velocity I'll denote by v0. Just 2. Not because it is 0, but just because it's initial velocity. Okay? So v0, so v0 is 0. So that's what drop means. V0 is 0. All right. Now you want to find out how fast this ball is moving as this ball is about to hit the ground. Mark my words. Not when the ball has hit the ground and all kinds of bad things have happened, but just immediately before the ball is going to touch the ground. So that velocity, we call it the final velocity, V final. Almost always noted as Vn. So your goal is to find out what is V final in this case. So let's say you want to do it this way. You want to go to different levels and drop the ball at 3 different levels, 4 different levels, it doesn't matter. And you're trying to figure out how it falls, what's the final velocity. So you can plot the final velocity, which is a dependent variable on the y-axis, and time it on the x-axis, because time is the independent variable, as we discussed last time. Question? No? All right. So at time t equal to 0, there can't be a final velocity which is more than 0 because I'm just dropping it. Right? I'm dropping it when I start the clock. And now say I take a reading at some time t1, let's say whatever seconds, and this is some number here. So let's give it some numbers, okay? So actually the way it will work out is if I do this thought experiment, or if I do a real experiment, and if I have a lousy stopwatch, so I don't make super good measurements, I can make a plot of time versus t final. So time would be in seconds, always put the unit down. There's no point writing something which has a unit if you don't write the unit along with it. So at time t equal to 0, you would argue that the final velocity is 0, just as we said, because we are just dropping it at that point. Now, at time t equal to 1, so 1 second that is, it turns out that you go out and measure the final velocity of the ball just as it's about to touch the ground. And it turns out, roughly speaking, again reminding you that we are not making very precise measurements, you'll find it's about 10 meters per second. As long as you're on Earth. If you go to the moon, the number will be different. And if you go to 2, it will be of the order of 20 meters per second. And so on. Okay? So it will turn out that if you actually make this plot, this will go like this, actually, through the origin. And at t equal to 1 second, this will be 10, roughly. At t equal to 2 seconds, this will be roughly 20, and so on and so forth. So if you do the experiment, which you can try at home, and you measure it, roughly let's say, you'll get it to. So that tells us something very interesting. That tells us immediately that we can actually describe this plot, because as I told you on Tuesday, any plot is an equation, right? So in this case, it's a straight line, so we know y equals mx plus b. So in this case, v final clearly is some kind of constant times time. As you can see, it's a constant because this line has a constant slope. Any questions? Have you lost me? How many of you have lost me? Only one person?
What's the name? You have parentheses there?
Nothing.
Oh, okay.
Just number 10. That was my question.
Where did you?
That was my question.
No real question? Yes.
Would you rather us use 9.81 meters per second or 10?
Not 9.1, 9.8. And it's not meters per second. So the contrast. But I'm giving you the rough slope. What is the rough slope? Can you tell me?
What's the what?
What roughly is the slope?
I don't know.
So the way you figure it out yourself, before me telling you, is this gobbledygook that I have here times time. Let's do a dimension analysis. What is the dimension of velocity?
Use it for seconds.
Dimension. I've written it here. You guys are not paying attention. Watch out. I'm going to catch you. You can't daydream in my class. Yeah? So L over T. That's the dimension. What is the dimension of T? T. So what should be the dimension here be such that left and right sides of the equation is the same? Louder. Come on. Yes.
What over?
No. Right. Left side has to be L over T. So what is something I need here?
L over T squared.
L over T squared. Good. Because if I don't have that, how am I going to match up the two sides? Now you see I have L over T on both sides. So L over T squared, this quantity is the dimension of acceleration. So you see, as the ball falls, this ball has to accelerate. So in other words, if I drop something towards the ground, and if I make a measurement of the final velocities, what nature tells me is that this final velocity is such that this ball has to be accelerating. So what does acceleration mean? Acceleration means that the velocity itself changes in time. And that makes sense. Because as you drop the ball, the velocity is 0. But as the ball is about to hit the ground, the velocity is v final. And as I told you, if you make measurements, you'll find that this v final is about 10 at t to the 1 second. The next second, it will be about 20. Third second, about 30, 40, and so on. So therefore, clearly, as you can see, that the dimension of acceleration comes in to make this equation work out, number one. Number two, acceleration here must be the way velocity changes in time. Mark you, I'm not saying speed changes in time. Velocity changes in time. And furthermore, its units would be meters per second squared and not meters per second, which is why I was telling you something else is wrong. All right, so normally acceleration due to gravity, which is because the ball is accelerating because of gravity, is denoted by the symbol small g. Never put capital G. Capital G in physics is a totally different meaning. Capital G is a gravitational constant. So small g is the name of the acceleration to gravity. And this number is approximately 9.8 meters per second squared. And that's the reason, since we don't use calculators in this class, we approximate that, and so can you, by 10 meters per second squared, as long as you know it's actually 9.8 meters. Question? Who lost? Yes.
Well,
Where did you have a net 20 from?
Good question. So that's obviously from measurement, right? So people have done measurements, and in doing the measurements, what you find is that the acceleration due to gravity on Earth is 9.8 meters per second squared. Is this acceleration truly a constant? Does anyone know? Is Earth truly a sphere? Yes.
It's not constant.
Why?
This Earth bulges out a little bit of the.
Yeah, so Earth is like a flattened sphere, right? Earth is an oblate sphere, right? So if you look at the Earth from outside, you will find that Earth has sort of flattening around the equator as it turns. Earth is mostly fluidic, so that's not a surprise. But it turns out that as a result of that, the poles are closer to the center of the Earth than the equator. So the acceleration due to gravity, we measure it very precisely, it's slightly higher, slightly lower in the equator because the equator is farther out than in the poles. So actually you will feel, if you measure your weight, not your mass, but if you measure your weight, then the weight will be slightly higher at the north and south poles, and the weight will be slightly lower in the equator and its vicinity. So the number actually varies ever so slightly from 9.8 something to 9.8 something else between the top and the bottom. Any questions? Okay. Where do you? So all right. So now this is the preliminary stage of this equation I've given you. I'm now going to make this equation into something a little bit more than what I've done. So suppose instead of dropping the ball, you actually throw the ball down. If you throw the ball down, let's say you throw the ball down at some initial velocity v0, and now v0 instead of being 0 is, let's say, 2 meters per second. Okay? So you actually push it down 2 meters per second. You will find that if the initial velocity here is 2 meters per second, at t equal to 0, it will be 2 meters per second because that's what you're, it hasn't left your hand practically, it's just about to leave. The next number comes out to 12 meters per second. It's basically 10 meters per second plus 2, and the next one is 22 meters per second, and so on. So it turns out that if you actually have an initial velocity, then it's v0 plus acceleration to gravity g times time. So this is the second kinematic equation. For now, I'll give it a semi-permanent numbering of 2. So if I say equation 2, you better believe I mean this equation for a while, which means I'll also get this equation 1. All right? So v final is v0 plus gt. G in this case is the acceleration to gravity. But is there anything special about the motion being vertical? So in other words, if instead of the ball falling, if the ball were accelerating along a horizontal line, then would anything be different? And the answer is no. So I can write v final equal to v0 plus acceleration times time as a more general version of equation 2. And if there is vertical motion, I can put acceleration a equal to g. Okay? Very soon we'll be using science. Right now I'm not telling you anything about science, but I will soon be telling you about science of the various quantities. But let's be clear that none of you have any issues so far. You should have some issues. No?
When you drop the ball, should we consider the mass of the ball?
It doesn't matter actually. That's a very good question. So, in fact, that's a very, very serious question. So, if you actually do the experiment in air, which you would if you drop something from the balcony, let's say, the velocity would have some form of dependence on mass. Why? Because it is the mass and the size which tie into how much frictional forces it will encounter from air. All right? So what we are doing in this case is to make life simple, we are ignoring the presence of air. which means that if you actually do this experiment precisely, you need to do this in vacuum. So you need to make a tall column. You need to take away as much air as possible, effectively making it into vacuum. And then it doesn't depend upon the mass at all. So that's a very precise statement. So it doesn't depend upon the mass. It also doesn't depend upon the size and shape or any such thing. Now, one of the things we are doing, which I haven't clarified yet, but somebody is playing with the phone. Yes, you. Don't try me. You'll not be allowed to take a quiz if I catch you from Tuesday. It's not that important. It's more important you get this, okay? If you don't need to take this course, you shouldn't be here. But if you are here, I assume that you seriously want to be here. So the thing is that we are assuming that whatever it is we are dropping is actually a point mass. So what is the meaning of a point mass? So we didn't discuss many of these, so I'm glad you're asking these questions because it gives me a chance to discuss. So a point mass is the mass of the entire whatever object I'm dropping, but concentrated effectively in one point. So for example, when you say my center of gravity is somewhere near my tummy, and let's say that's 3 meters from the ground, it turns out that you can replace yourself for mechanical purposes approximately by a point mass in your tummy at that position. And the laws would work out just fine as if you hadn't done that. Unless, of course, you are jello, in which case there are other complexities. But we'll come to that much later. Okay, but that's a very good question. Any other questions?
If you threw a ball up in the air, would the velocity be the same? Would it be constant velocity? Or would it,
When?
if you, let's just say, threw a ball up in the air and then caught it again, would it stay constant or would it be different?
So as the velocity, as the ball goes up,
Yeah.
which way?
Then it comes down.
Yeah, but which way would gravity be as it goes up?
Yeah.
Downward, right? Gravity doesn't go upward. So it'll slow down because gravity will be pulling it down. So it'll go up, but before it flips direction, its velocity for a very, very tiny span of time should be what? 0. Because the velocity goes like this, stops, comes. Actually, if you don't have air, if you throw it with velocity, let's say 10 meters per second, if it comes right back, it will again be 10 meters per second, excepting that initially it will be upward, coming back it will be downward. And the reason why the direction flips is because gravity is continuously pulling it down. So we'll do that. Actually, we'll do that very soon. Any other questions? Yes?
So is it always velocity, so negative?
We'll come to that. Yeah, that's a very good question because we'll get to science. I'll teach you how to do science. In fact, that's a multi-stage process. All right. So let me now deal with the thing I did with the average velocity because there's something to be said there. I've given you equations 1 and 2. I now want to construct what would be equation 3. Again, semi-permanent for now. So in equation 3, what I want to find out is ratio of distance traveled. So you see, I told you that from some level here, you drop your ball and the ball falls. And we talked about the final velocity here, we talked about the initial velocity here, we talked about the fact that there is gravitational acceleration which would be downward, which is why it's speeding up. These are things we have explicitly or implicitly already gone through. But we haven't talked about the fact that how can we figure out what is the height of this level. Let's call the height y. Because it is vertical, we'll call it y. When it is horizontal, we'll not call it height. We'll call it distance, and we'll typically denote it by x instead of y. Okay? So, just so that you know, this is not always y. When I write y, I am implying that this is a vertical distance that's being traveled. All right. I already know that y must be v bar times t. How do I know that? Which equation is that? What? Okay, so courtesy of equation 1, I already know that, right? So how do I know what the final velocity, what the average velocity is? So average velocity computation here is quite simple, because I know for a fact that if I plot the time versus velocity, the velocity would somehow go up, right? Whatever it is. So in general, this is a V0. Some other point in time when it reaches this bottom, let's say it's V final. So I can always say V bar is V0 plus V final, and since I only have 2 points, V0 plus V final by 2. Okay? So that's my average velocity. So in other words, I should be able to write this height y, which I don't know, as V0 plus V final over 2 times time, where t is the time of fall, how long it takes for it to actually come down and just about hit the ground. Now, this is fine. There's no problem here, but we can do a little bit better. The reason why we can do a little bit better is because equation 2 implies that v final is the velocity I initially had v0 plus gt in this case, g being the acceleration due to gravity. You can make it at if you wish. It doesn't matter. I'll stick to g because right now we are doing a vertical problem. So I should be able to write v0 plus, instead of v final, v0 plus gt, because that's what v final is, divided by 2, put the whole thing in bracket and time. Okay? Any questions? You okay with it? Cool. Sure? I didn't make a mistake? I will make mistakes for you to catch. Yes?
Does it say Vx equals V0 plus GT?
Yes. But that was not a question. Legitimate question? No? Okay. So what do I do? Well, I can do this. I can see that there are 2 V0s here if I open this bracket. So if I add them up, it will be 2 V0 plus GT, right? Divided by 2, because that 2 is still sitting there times t. Okay? So I should be able to then write y. I'm walking you through the steps, but I won't be walking you forever. 2 V0 over 2, because that's what the ratio here means, gt over 2 bracket times t. Any problems? Is that correct? Is this correct?
You can simplify it.
Yes. So we should, right? There are 2 sitting above and below, you must get rid of them. So therefore I should be able to write v0 plus 1/2, actually v0 t plus 1/2 g t squared, because I have to multiply with these 2 both terms. So this is an equation that I'm going to get, which will now be my equation 3. Again, a semi-permanent name for this equation. So therefore, I have arrived at a kinematic equation. I'll now start to box them. So the first one was this. That was equation 1. The second one was on this board. So let me just momentarily bring it down. That will be both of these. They mean the same thing. And the third will be this, or alternately, if I have horizontal motion, then instead of writing y, I might write x or y, it doesn't matter, or whatever symbol I give it, doesn't matter. I can call it v equals v0t plus 1/2 at squared. By v, I mean a general distance, and this is a general acceleration, and this is what we got. One of the things we have tacitly assumed so far is what? What is it that we have assumed that we didn't question at all? Does anyone have any clue as to what I'm asking? Yes, that is one of them. And there is no air, because there is no, we have not considered air resistance. But there's something else which is a little bit mathematical that we have assumed. Yes?
That there isn't another force acting on the ball drop?
Say that again.
That there isn't any outside force acting on the ball drop?
Yeah, that's okay. That's a fair assumption. That's not a big deal. But one of the things we have assumed is that the acceleration is constant, because that's the reason why we are using the example of the Earth. Because when we are in the gravitational field of the Earth, the acceleration turns out to be 9.8 or so meters per second square. So that's a constant acceleration. But acceleration, does it always have to be a constant? Can acceleration vary? You're driving a car, you can vary your own acceleration, right? You can accelerate a little bit. Somebody is giving you a hard time, you accelerate and catch that guy and scold him or her, and you can do those things. So acceleration is something that can vary. However, here we have assumed that acceleration is actually a constant. Now that's a pretty big deal. So everything that we are doing in kinematics, which is what I wrote on the top left of the upper board there, typically assumes acceleration is a constant. So in kinematic studies, this is a simplification that we do, which we will remove in about a week and a half, or maybe 2. So if I remove the fact that acceleration is not constant, what do you think will happen? Does anyone have any idea? Not necessarily. But there's something fundamental that happens when acceleration is not constant.
Would you just take the average acceleration?
No, that's what he was also saying, which is not. Look, it turns out, as we will see, and I want you to kind of be aware of this because it makes our journey a little easier as we go there. The presence of acceleration means there is the presence of a force. We haven't talked force yet. Gravitational acceleration g comes because Earth exerts gravitational force on us. So whenever acceleration is constant or varying, in general it means there is a force acting on the object. So by assuming that acceleration is constant and dealing with those examples in kinematic equations, we are removing the various complexities that would emerge when we introduce force, because we must introduce force laws to deal with them, and those are the Newton's laws. So we'll come to that I think around chapter 4 or so. Right now we're in chapters 1 and 2 of the book. So acceleration right now is constant. So we have done a good bit of what I had planned, but we'll now take off and do something very important. Now, one of the important things that I want to do is that if you take inventory, you see that we have learned how to calculate the height or the distance in a problem with accelerated motion. We have learned how to relate it to acceleration velocity, let's call it A or G. We also know how to calculate final velocity. And in all cases, we must have information about time, right? Because if you observe equations 1, 2, and 3, they all involve time t. None of them are devoid of time. Suppose you don't have any way of knowing time. What can you do? Does it mean that you are stuck and you can't do anything else? The answer is no, because we can actually derive an equation which turns out to be very useful, which doesn't explicitly use time. So suppose I start from the fact that T final is B0 plus GT or AT equals my equation 2. So in that case, I can immediately say that GT is, if I take it to the other side, V final minus V0, which would mean that T is V final minus V0 divided by G. So I can express time in terms of the velocity difference, v final minus v0, divided by the acceleration due to gravity in this case. So that's an expression for time. What I can also do is I can now go back to equation 3. Equation 3 implies, let's say y is v0 times t plus 1 half gt squared in general. Right? So I should be able to write v0 if I want to get rid of time as v final minus v0 divided by t plus 1 half g v final minus v0 over g, which is time. But now time has to be squared because this term is squared. Any problems? Any objections? Anybody needs a clarification? No? Everything is okay? So what we'll do is we have to now simplify because this thing looks pretty ugly. Simplification in algebra is difficult. And one of the things that I will be testing you a lot on is your ability to simplify. Because if you can't simplify, you typically cannot do them properly. You'll make unnecessary mistakes which will really affect your performance. So what I'm going to do, what do you see common in both the terms? On the right hand side.
You have to minus it down.
Very good. So that's something common in both the terms. So what I can do is I can actually take v final minus v0 over g common. And then the first term would be just v0 because that gives me v0 times this, which is that term there. The second term would be 1 half. I've taken out one of the g's, so therefore I don't have a g anymore. I'll have v final minus v0. Are you okay with me? Anybody thinks I made a mistake? Did I make a mistake? Are you sure? Check it.
Yeah, I thought it was a G.
You still think I missed it? Anybody else thinks I missed the G? Do you think I missed the G? But how many G's are here? There's no cancellation between those G's, they don't talk to each other? They do?
No, I got it.
Okay.
Yeah, I got
So
it.
I've actually done G over G squared equal to 1 over G, so it's here.
Yeah, I got it.
I don't have a G inside. Are you sure? Let me try. Sure. I'm very good at tricking people. That's what I do for a living. Half the time. Alright. So I should be able to. Can I put this G on the other side? Can I put the G on the other side? What is that called? What is the mathematical step called? Cross multiplication. So what I'm effectively doing is I can multiply by G both sides of the equation and then nothing would change. So if I do that, then I can put Gy on the left side. I can banish this G from the right side. The v final minus v0. And then over here, I have v0 minus 1 half v0 as I open the bracket, plus 1 half v final. So what I can do then is I can write v final minus v0. I can shove 1 half outside and get a v0 plus v final. How many of you lost me? Yes. Why did you lose me? I haven't done anything bad. Yes. Tell me.
I think just like the math.
Okay. What about you? What?
I could be very wrong, but isn't VF minus VC supposed to be squared?
It was. But I took V final minus V0 over G common to the two terms. So, remember? So here, it is squared.
Because it's in parentheses, it was squared outside. So, yeah.
V final minus V0 over G squared, right?
Is it G that's only squared or VF?
Well, you have to think of it carefully. There is a G on the top, there is a G squared below. So there is really one G below, right? Between these two terms. And there is a V final minus V0 squared, right? So what I've done is I've taken V final minus V0 over G outside. So I've taken care of the G. So I'm left with a V final minus V0 because I have to square the V final minus V0 as above. Do it yourself, you'll figure it out. It's much easier. Just do it now. Just repeat the steps in your notebook. Don't look at it, just do it. You will know what I mean because it's a step that is a little bit tricky. All right. Any other questions? So what is A minus B times A plus B? A minus, so this is algebra, right? This is daily algebra. A minus B times A plus B, if you multiply out and check it out, it's A squared minus B squared because the minus AB and the plus AB terms, if you cross multiply, they cancel out. Alright. So therefore, if I have Vf minus V0 and V0 plus Vf, I should be able to write 1/2 B final squared minus V0 squared. Which means I should now be able to write an equation V final squared is V0 squared plus Gy. Sorry, plus 2Gy. Because I have to take this my 2. And so this is going to be my equation 4, semi-permanent numbering. And then I should also be able to write V final squared is V0 squared plus 2 acceleration A1, depending upon whether acceleration is horizontal or vertical or whatever. So these are the 4 equations that you need to know, be able to derive and memorize this point onward. Because you're not getting a cheat sheet, you must know this cold turkey. There is no excuse for not knowing it. And if you don't know it, you'll most certainly not make it to this class, unfortunately. But I'm sure you'll figure out a way of. But my suggestion to you is, please, for heaven's sake, don't blindly memorize this. Because so many kids make a mistake as follows. They would write everything correctly and forget to square something because they don't understand what that squaring means. They haven't done the checking of dimensions that I taught you on day 1 and repeated on day 2. So if you don't do them, you'll pay a price. And that is a mistake, which is going to cost you. So my suggestion, when you write an equation, figure out what it means, where it comes from, spend time on it. Equations tell a story. An equation is telling you a great deal of information in a very compact form. So that it's telling you a story. You got to know that story. You got to remember where it came from, just like you would read a story and remember what the story says. And to make sure in physics, if your story is correct, which you can't do in other subjects, you can do dimensional analysis for your own sanity check. So these are the steps that you must make. You must learn to make. Because if not, it'll cost you. It'll bite you unnecessarily. And I don't want you to go there. So don't try to act smart. It doesn't help anyone. Make sure that you can derive these just the way I've derived. Otherwise, I would have asked you to read those equations up. Go through all the steps. Make sure you can do it yourself. And understand if something is square, something is not square, what it physically means, and why should it be so. Okay? Somebody had a question. You had a question? Yeah.
The y in the equation shouldn't be d.
I called something a d before, but I changed to a y. Normally one uses y as opposed to a d. Yeah. Vertical distance is y. Horizontal distance can be x or d. So, oh, this one?
Yeah.
You are right. I'm sorry. Yeah. This is x.
Any other questions? Yes.
Between gy equals df minus d0, d0 1 half plus 1 half df, where do the 1 halves go?
1/2 is right there.
I see the 1 half pulled out, but how does that happen?
You mean here, right?
One above that.
Here?
Between the one above that and the second one.
Here?
Sorry. The second one down from there to the next equation. Where does, where do the 1 halves go?
This half?
Yeah, where does that come from?
This half came from here. V0 minus
1 half.
half V0 is half V0, right?
Yeah.
And there is a plus half here. So I just took both the halves out and put it there. And I made it V0 plus. Because this is V0 plus Vf divided by 2. From here. Right?
Like if you pull the like 1 half back, it's give you some V0. So we got like V0 minus like a pass or V0 whatever. Then you take the 1 half off. Like if you pull the 1 half back in that formula, we just use some V0. So like the first one.
Say that again.
So like you just pull like 1 half back.
I didn't pull anything back. I just computed V0 minus half V0, which became equal to 1 half V0. So I didn't take anything away. I combined the two marks, right? Otherwise you have a half-baked story. Any other questions? Yes. Could you do it?
Yeah, I got that first.
Okay, good.
Where did the G go in the other things?
I put the G on the left side.
Okay, but on this side.
Did I miss a G? No, I didn't miss a G. I put the G here.
Are you supposed to do it on both sides?
I did. See?
It cancels here, but what about the other bracket?
So that became a GY. And if you multiply by G, the G and G cancel out.
No, I'm talking about those brackets.
Here there is no
Yeah.
G. All my G's have been managed. I have only one G in the denominator effectively. Because that had one G and this had a G over G squared, so that was another one G. 1 over G.
Ask you that.
Okay. Anybody else? Any questions? Alright, so from tomorrow, you know these things very well. Let me give you a brief thing on significant figures because that's important for us since we don't use calculators. So, most of you have learned significant figures in some course or the other. It turns out that the use of significant figures may slightly differ between disciplines. So, I just want you to be absolutely aware of what we mean in physics and in general by significant figures. So let's talk about precision and significant figures. So in significant figures, the reason why this is an issue at all is because no measurement is perfect. Suppose I measure a length between two walls, and suppose I measure it with some tape or ruler or what have you, and it turns out that in one measurement it's 1.84 meters, in one measurement it's 1.83 meters, in one measurement it's 1.87 meters, etc. So in other words, what I'm trying to tell you is something very important. No measurement is perfect. All measurements have errors. Okay? So this is a very profound realization for us as scientists that when we give a number, we have to be very careful. You can't say that a number is absolutely precise. Science in general, it doesn't matter if you're in physics or biology or chemistry or geology or earth science or astronomy, any measurement that you make is by definition imperfect. What I'm trying to tell you is that perfection is unattainable.
All right? So because perfection is unattainable, what we try to do is we try to be as precise as possible. And hence, the issue of precision and the issue of significant figures. What do we mean seriously as something we really know? And what do we mean seriously as something that we sort of know? We distinguish between. So here, when we take all these measurements, in a very simple case, you can say, let's say if I average all these numbers, I take more and more measurements, let's say, it's 1.85 meters plus minus 0.2 meters. So this is my uncertainty. That means that depending upon the measurement I make, depending upon perhaps the ruler I use, depending upon the time of the day, depending upon, whether there's been an earthquake or not, this length can vary slightly. And the average length that I have is 1.85 meters, and that's the level of uncertainty I have, 1.85 plus minus 0.2 meters. Precisely spoken, that means that this number can be between 1.83 meters and 1.87 meters. It will seldom be outside this bound. All right? So all measurements are like that. And you can do a simple thing. You can measure your height laying down, have somebody measure you laying down, and standing up. When do you think you'll be taller? Yeah, because you're turning or driving. If you go to the space station, what happens to you? Your height changes. Your height changes in a very significant way. Why is that? Your bones are not like what used to be on Earth anymore, because there is no gravity. So actually what happens is that your body realizes it doesn't quite need the same strength in the bones anymore. And as a result, what do you have? Have you read about it anywhere? You have bone loss. So one reason why the astronauts have been up in the space station for a year or more is because we want to understand what space travel does to the body. Like it or not, we will be doing space travel much more than we are doing now. So any kind of space travel requires you to be out in zero gravity or low gravity environment for exceedingly long time. And what that means is that your body actually may become unfit for operation, whatever operation that you need to do. Suppose you go to a planet which is larger than Earth. You get down, and all your bones immediately break. That won't be fun, right? That will not only be painful, you won't be able to go to a doctor because there is no doctor in the nearby planets either. And you're screwed. Think about it. So, it turns out, therefore, that measurement is very important. We need to understand how bones behave. Numbers vary, so on and so forth. Anyway, I don't want to get off track. But when we write this, we can write it as follows. We can write it as 1.8 meters, let's say. And this means that I know this number and I know this number. So this has two significant figures. Suppose now I change my unit. I write it in kilometers. So that will be 0.0018 kilometers. Because I divide it by 1,000, right? 1,000 meters make a kilometer. So 0.0018 kilometers. The number of significant figures here, and pay attention because if you screw this up, you'll be in trouble. I will actually penalize. Number of significant figures must be 2 here. Number of significant figures must be 2 for the following reason. Just by changing units, I can't make my measurement more precise. That would be insane, right? Do you agree with me there? I can't change the units and make my measurement different or more precise. So obviously it has to be 2 significant figures. We also realize that these 2 zeros here that depend upon the choice of units. So therefore, zeros before the significant number don't matter. Uh-oh, turn your phone off, throw it away. Come on. This is why you're supposed to turn the phone off, as I mentioned in the very beginning. So 1 and 8. You have two significant figures. So zeros before don't matter. Now suppose I actually knew it precisely until this point only, 1.80 meters. Suppose it was 1.802, 1.807, 1.798, whatever, such that I could be certain. Well, I'm sorry. Suppose it was 1.801, 1.804, 1.800, 1.799. All these were my numbers. Well, this won't work. This would. So anyway, I can say for sure in that case, in this case, that I have 3 significant figures. So if I have 3 significant figures going from meters to kilometers, I would make it 0.00180. So now you see how many significant figures do you think that the second case has? 0.00180. 3. So in other words, what I'm trying to tell you is that this 0 after, 0 or zeros, after the number, is significant. So you have to be careful. If I tell you that that 0.430 or 4.300, that means I actually know 4. I actually know 3 on the other side of the decimal. And I actually know those 2 zeros. So there are 4 significant figures. You can't throw away those zeros saying, oh, I can throw away the zeros. No, you can't do that. Okay? But you can throw away these zeros. Zeros before the number. Because they come around because of the choice of measurement that we do. Any questions? All right. Assuming that you'll never screw this up, I'll move forward. Please come prepared for the quiz, okay? You get 22 quizzes, they add up to 50% of the course grade. Everything that I've done is fair game, including all the homework problems I've seen. And there are no partial credits, no nothing. So please be careful, take them seriously. All right, so suppose I have a number which is 1.043. How many significant figures do I have here? 4. Suppose I divide it by 2.0. How many significant figures will I have here? Huh? 2. So now this number, whatever the result is, only has 2 sig figs, and the reason is that I actually optimized this number by dividing it with a less precise number. So my answer would always end up being less precise. So that's the point. So both the numbers have to have the same precision for you to be able to maintain the precision. If all your numbers don't have the same precision, then you are reducing the precision of your calculations. The other thing I want to say is that, having said this, in reality, when you do a calculation, let's say for a problem, you will find that precisely sticking to the significant figures will actually make some calculations super simple. Okay? So, in other words, you may not get quite the right result. So, in other words, what I'm trying to tell you is that when you actually do your calculation, be a little bit generous in carrying through the erroneous digits until you can make sure that you actually don't need them for any estimation. So in reality, for most of the problems that you will do, you will find that sticking very strictly to significant figures may actually not work, may actually not give you the answer that you're looking for. It may give you an answer that's super simple. Your real answer may be 2.5, but having to stick to the significant figures very accurately might give you a number that is just 2. And that's a very major difference compared to the number that you should be getting. These things happen in real life. So significant figures are used with a tiny dash of discretion. That said, you shouldn't keep 23 significant figures or an unreasonable number of significant figures in any calculation, because that would be deemed as incorrect. But if you make it super simple, you can end up making an unnecessary error. Now, in the last few minutes, last 7-8 minutes, I want to do a relatively simple problem. And I can show you how to do these problems in a systematic way. So suppose I'm told that we go back to the problem that we started. Somebody's been dropped to the ground from some height. Okay, so here you are dropping the ball, and suppose you are interested in measuring this height here. Let's call this height y. And we know that because this is falling vertically, the acceleration downward is due to gravity, that's g. And we also know that we are dropping the ball, so v0, let's say, is 0. Because I'm telling you, you are dropping the ball. Okay. And what I want to find out is how tall, or what is y? That's what I want to find out. What is y? I also want to find out what is the final velocity we find. So these are relatively straightforward problems. I won't be giving you problems quite as simple. But these are relatively straightforward problems, and I want to find these out. The way you do these problems is following a certain code of ethics. What is the code of ethics? First, you write down what you know. So this is something that you must do for every problem, and if you don't, I'll catch you. So write down what you know. This is W. Okay. So you know for a fact that V0 is 0 numerically because this is accelerated. This is the velocity as you are dropping. You also know that the acceleration here, which you are calling g, is, let's say, 9.80 meters per second squared. Let's keep the number for now. And suppose I told you that this ball is falling for 2.5 seconds. So in other words, I told you that t is 2.50 seconds. We will now impose an extremely important thing for us. And we will impose a sign convention. And we will stick to this sign convention for the next 1 month or so. So do not make a mistake in there. So anything that goes upward or an upward direction will be positive. Downward will be negative. So therefore, since g is acting downward, we'll put a minus. Alright? So write down what you know, step 1, and then write down all the kinematic formulas that could be relevant. So I would write down, for example, y is v0t plus 1/2 gt squared. I would write that down. That's why you need to memorize them. I would write down v final is v0 plus gt. And I would write down v final squared minus v0 squared is 2gy. I would write this down. I can also write down that y is v bar times t. I don't know what I mean. But these are the 4 equations. This is where memorization is important because you need to know them and you need to know them correctly. You do everything right, forget the squares, I'm not going to be very kind. You're still going to get a 0. So this is the first set of steps you must take. List what you know and list what your weapons are. Those 4 are your weapons. Now if you do this problem, the first one is very easy to do, which is to find out what is y. And you can see that to find y, since you know time, you can just use this one. You don't have to go there because you don't know v final. So I can simply write y, v0 is 0, g is minus 9.80 meters per second squared. Sorry. Don't forget to write the units. That's mandatory. Times t squared. T squared is 2.50 second whole square. So I can write this approximately as minus 10 meters per second square, and 2.5 is 5/2. So I can approximate that as 5/2 seconds squared. So therefore I should be able to write this as minus 10 5 squared is what? Don't fall asleep. And 2 squared is 4. So this is basically 5 squared, this is 4, 10, 4, let's see, where do you correct me? Times 10. Oh, I forgot a half here. That's something that you funny. You guys didn't catch it. So therefore, this is going to come out to first of all a negative number because y would be downward. I have taken the velocity to be 0 here. I have started here, and then I'm going down. So therefore, y should be downward because this is 0 of y. So this number will come out, if you do the calculation, to be 125 over 4 meters. So 125 over 4 meters turns out to be roughly minus 31 or so, 31.2 actually meters. So this is the first part of the problem. Second part of the problem you can do yourself. I'm not going to do it now. I'm kind of out of time. But second part of the problem you can just get the following. So let me quickly cover that. Second part of the problem would be I'm looking for V final. So V final I can already extract from this one, the second formula, simplest one. V final is V0 plus GT. V0 is 0, so it's GT. Again, this is minus 10 meters per second square. T is 5 over 2 seconds. 2.5 seconds, basically. So therefore, it's 50 over 2, so that's approximately minus 25 meters per second, not second square. Second square, 1 over second square, and second will adjust to 1 over, yes?
Isn't that wrong?
What?
You put 10 over 2 times, so like on the
There was a half here.
yeah, so I think that half is supposed to be there. So the answer should be 62.
No. This is the formula I'm using. So it's a half GT squared.
No, I mean,
Right? So it's a half G T squared. So half. So this is 5. And 25 quite. Yeah.
Oh, never mind.
Yeah, good. I forgot the half when I wrote it for the first time. Any other questions? Yes?
Tell me that gravity is what 9.8 turns on negative every time you use it in one place.
For now.
And it's going down?
For now, yes. We'll assume that. Okay. So, any other questions? Calm down. I'm not done yet. Calm down. It's 10:48. You still have 2 minutes. Any questions? If there are no questions, you can now leave.